Jai Jagannath. Welcome to More Physics. And today, this is the last lecture of capacitor and dielectric. So here we will solve some numericals, particularly from University Physics book. So first, let us discuss example 24.10 and 24.11. So both problems are same and extended. Now, you see, a parallel plate capacitor. So this is a parallel plate capacitor. Okay. So here area of the plate is given 2000 centimeter square. So you know 1 centimeter square is equal to 10 to the power minus 4 meter square. So that means we got area of the plate is 0.2 meter square. Then distance of separation is given. Distance of separation is given 1 centimeter. So that is 0.01 meter. And this capacitor is connected to a supply and charged to a potential of 3 kilovolt. And this capacitor is charged to what potential difference? 3 kilovolt. So this is the original initial potential difference across the capacitor. That means it is charged to this value. Now what will happen? Suppose initially this is a switch. This capacitor is charged. This is positive charge, this is negative charge. So initially the switch is in what position? Closing position. Now initially the switch is in closing position. So now what will happen? After fully charged to 3 kilovolt, then we will disconnect the switch. So after disconnecting the switch, we will introduce a dielectric. We will introduce a dielectric medium. Okay. So whose dielectric constant is K. So we have to find that. Then after inserting the dielectric, the potential difference decreases to 1 kilovolt. So after dielectric, the potential difference reduces to what? 1 kilovolt. So this is the situation. So you have to calculate original capacitance. So first we need to find what is the value of original capacitance. So what is original capacitance? Original means initial capacitance when it is connected to the supply. So here C naught is equal to epsilon naught A by D. So epsilon naught, what is the value? 8.854 10 to the power minus 12. Area, this is 0.2 meter square divided by distance of separation 0.01 meter. So you calculate this, you will get the original capacitance, you will get 1.77 into 10 to the power minus 10 farad. So this is the solution of first bit. We calculated the initial capacitance before connecting the dielectric. Come to second bit. What is second bit? Charge on each plate. Charge on each plate. So you know the formula. Q is equal to CV. So original charge, initial charge is equal to initial capacitor and the initial voltage. So what is C naught? It is 1.77 10 to the power minus 10 farad into volt. So what is the initial potential difference across the plate? It is given 3 kV, 3 into kilovolt, that is 3000 volt. So now you calculate, this is the, after calculation you will get the result is 0.531 microcoulomb. That is 0.531 into 10 to the power minus 6 coulomb. Okay. So next, third bit. Third bit we have to find capacitance after inserting the dielectric. Capacitance after inserting the dielectric. So we know the capacitance value C is equal to Q by V. Now see, when we are disconnecting the supply, the charge will not going to change. Charge remains constant. That is, charge value remains this. But potential decreases to 1 kilovolt. So now what is the new capacitance? So C is equal to Q by V. Q is nothing but the initial charge that will not change. But potential difference is now V dash. So what is V dash? So that is equal to 1 kilovolt. So Q naught is equal to 0.531 micro. Micro means 10 to the power minus 6 divided by new potential difference developed across the capacitor is 1 kilovolt, that is 1000 volt. So now you just calculate. I think it will come 5.531 10 to the power 6 by 1. So 531 picofarad. Pico means 531 into 10 to the power minus 12 farad. So this is the answer. So now, you see that we have already calculated the capacitance. We calculated capacitance and initial charge and the final capacitance after introducing the dielectric. Now we will find what is the dielectric constant of the medium. So now you know C capacitance is equal to K times the air capacitance. Capacitance for any medium is K times the capacitance of the air capacitor. So that implied K is equal to C by C naught. K is equal to C by C naught. Okay. So that is equal to the new capacitance now 531 picofarad divided by initial capacitance is 177 picofarad. So just take the ratio, you will get 3. So this is the dielectric constant of the dielectric medium. Then fifth bit. Fifth bit is what? You have to find the permittivity of the medium. So permittivity is nothing but epsilon is equal to epsilon naught into epsilon naught. Epsilon naught into epsilon r. So epsilon r is nothing but the dielectric constant. It is K times epsilon naught. So that implied the permittivity is equal to K. So what is the value of K? So K value is equal to 3 into epsilon naught 8.854 10 to the power minus 12. So if you will calculate, you will get 2.66 into 10 to the power minus 11. And you know the unit of epsilon naught is coulomb square by Newton meter square. Or you know the epsilon naught unit is farad per meter. So I have explained how it is farad per meter. So now the fifth bit. In the fifth bit, you have to find what? Just go to the question. So here dielectric constant dEF. So you see. So here you have to find the induced charge, that is Qi, induced charge on dielectric medium. So this theory I have already discussed in this theory part. So you can refer the previous note so that you will get the induced charge is equal to charge on the capacitor into 1 minus 1 by K. So this formula I have already discussed in the theory part. Just refer. So this is the induced charge due to dielectric, and this is the original charge in the capacitor into 1 minus 1 by K. So that is equal to Qi is equal to Q. So what is now our charge? So our charge is 5.31 into 10 to the power minus 7. So this is the, you see, charge remains constant. So when you are disconnecting the supply, charge will not get the path to discharge. So initially whatever charge is there, now after introducing the dielectric, same charge will persist. That is 0.531 microcoulomb. So you can say it is 5.31 into 10 to the power minus 7. So into 1 minus 1 by K. K is equal to 3. So just to calculate this, I think it will come 3.54 into 10 to the power minus 7 coulomb. Next, Next bit, what is the original electric field between the plates? What is the initial electric field? You know, electric field intensity can be found out between the potential gradient V by D. Since it is original, that is initially, that is in the air medium, the electric field is equal to V naught by D. So what is the initial potential difference across the capacitor? 3000 volt by distance of separation 0.01 meter. So that is equal to 3 into 10 to the power 5 volt per meter. Next, next, next we have to find the electric field after dielectric is introduced. So electric field after insertion of the dielectrics, that is V by D. Now you see, so after inserting the dielectric, what is the voltage across the capacitor? What is the potential difference across the capacitor? It is 1 kV or 1000 volt divided by distance. So that is equal to 1 into 10 to the power 5 volt per meter. So this is the electric field. Okay, or you can calculate, E is equal to sigma by epsilon naught, epsilon r. Okay, so that is equal to sigma is q by a, epsilon naught, epsilon r is k into epsilon naught. So you know the charge and you know the area of the plate and put k, put epsilon naught, you will get the same result. Same result. So next is your find what is the question? The electric field after dielectric is inserted. Find energy stored and energy density before and after dielectric is introduced. Okay. So now see energy stored is equal to U naught is equal to what? Half C naught V naught square. So that is equal to half C naught. What is the initial capacitance in the air medium? 1.77 into 10 to the minus 10 into initial voltage is 3000 volt square. So if you will calculate, you will get 7.97 into 10 to the minus 4 joule. So this is the initial energy stored across the capacitor before introducing the dielectric. Now after introducing the dielectric, what is the energy stored? So it is half CV square. So half capacitance is already increased by 3 times. So 3 into 1.77 into 10 to the minus 10, 3 times of this initial capacitance into voltage is already decreased to what? 1000 volt. So 1000 square. So now that means the energy stored will be reduced by what times? K times. So if you divide, it will get 2.66 10 to the power minus 4 joule. Or you can write this is divided by 3. So you will get this result. Okay. So now this is the energy stored. Next, energy density. So energy density is written as small u, and energy density in the air gap, it is equal to total energy stored for the volume. So total energy stored is equal to what? 7.97 10 to the power minus 4 divided by volume. Volume is equal to area into area of the plate into distance of separation. Okay, because within that area whole dielectric will be there. So what is the volume of the dielectric medium? Area into distance. So what is the area? 0.2 meter square. What is the distance? 0.01. So you just calculate. I think it will come 0.398. And since it is energy density, unit is joule per meter cube. Then after introducing the dielectric, what is the energy density? Energy density is equal to total U by volume. So total energy stored is equal to 2.66 10 to the power minus 4 divided by volume area into length, that is equal to 2.66. Okay, just calculate this. I think it will come 0.133 joule per meter cube. Now see, This is example 24.6. Question is, in this circuit, you have to find equivalent capacitance across A and B. Okay. Also, you have to find potential difference and charge across each capacitor when 9-volt source is connected across A and B. So what you will do, for simplicity, you have to give the name of variable point. You see, let us say this point is A. So if this point is A, this point is also A. This point is also A. This point is also A, because this is common point, common potential. Okay. So now you see this point, this point, this point, all are having same potential. Let us say give the name of this is equal to D. This point is D. So now you see the what is the voltage source connected across A and B. So across A and B is equal to 9 volt. So what we will do? So first reduce the circuit. First reduce the circuit. You see, in from A to D point, so these two capacitors are connected in series. So first take the equivalent of 12 and 6 which are connected in series. You see, let us say this is my point A. From this A point, this is what? 11 microfarad capacitance. This is what? So this is your 11 microfarad. Now, across this path, you see 12 and 6 are connected in what? Series. So what is the equivalent capacitance? 12 into 6 by 12 plus 6. That is equal to, I think it will come 4 microfarad. So 4 microfarad. So 12, 6 are in series. Its equivalent is 4 microfarad. And along this path, there is 3 microfarad. And this point is our D. And this is connected to 9 microfarad. Okay, this point is B. So now again we have to reduce. You see, 3, 11 and 4 all are connected in parallel across A and D path. In between A and D path there is, this is one path, this is second path, this is third path. All are connected in parallel. So you know, for parallel connection, what is the equivalent? Equivalent is nothing but sum of individual. That is 3 plus 11 plus 4. That is 18 microfarad. So which is nothing but sum of 3 plus 11 plus 4 microfarad. And this point is D, and this is your 9 microfarad. This 9 microfarad is connected between D and B. Okay. So now what is the question is find what is the equivalent capacitance across A and B. So now this is A, this is B. So if I will connect a source, if I will connect across the source, okay. So in that source the charge will start from this point, and this charge through this and this will remain same. So that means these two are in series connection. If it is series connection, then what is the equivalent capacitance? So equivalent capacitance is equal to CAB is nothing but this and this are series, that is C1 into C2 by C1 plus C2. Okay, so you know 1 by equivalent capacitance C is equal to 1 by C1 plus 1 by C2. So equivalent capacitance will be C1 C2 by C1 plus C2. So that is equal to so what is the value of C1? 8 microfarad into 9 microfarad divided by 18 plus 9. Just calculate this. I think it will come 6 microfarad. So this is the answer. So what is the equivalent capacitance across A and B? This is the equivalent capacitance across A and B. This result we got. Okay. So next, what will find? We have to find the total charge supplied by the source. Now see this A and B terminal. The potential difference across A and B is 9 volt. Suppose this A and B is connected by what voltage? 9 voltage. So if so, then what is the total charge sent by this source? So you know the total charge Q is equal to total capacitance into total voltage. So what is the total capacitance across A and D? So I can write in this way: charge across A and D, charge across A and B is equal to capacitance across A and B and voltage potential difference across A and B. So that is equal to capacitance across A and B is equal to 6 microfarad into supplied voltage. The voltage across A and B is 9 volt. So that is equal to, so that implied total charge across A to B path is equal to 54 microcoulomb. So this is the total charge sent by the source. But we have to find the charge and potential difference across each capacitor. Now see, what is the charge across this 18 microfarad? It is 54 microcoulomb. Then we have to find what is the voltage across A and D. So you know V is equal to Q by C. So voltage across A and D, VAD, is equal to charge across A and D and capacitance between A and D terminal. So here, what is the charge across A and D? It is nothing but same charge, 54 microcoulomb, because in series connection, charge across each capacitor remains same. So here charge across 18 microfarad is 54 microcoulomb divided by capacitance across A and D is equal to 18 microfarad. So that is equal to 3 volt. So voltage across A and D is equal to 3 volt. Okay. Then what is voltage across D and B? Voltage across D and B is equal to similarly charge across DB by capacitance across DB. Charge is nothing but 54 microcoulomb divided by capacitance is nothing but 9 microfarad. So that is equal to 6 volt. Just cross check whether it is correct or not, because the total supplied voltage is equal to 9 volt. So this 9 volt is equal to voltage across this plus voltage across this. Already voltage across 18 microfarad we have got 3 volt. So definitely voltage across this will be 6 volt. 6 plus 3 is equal to 9. Okay. So now you see the voltage across A and D, voltage across A and D, we got voltage across A and D, we got 3 volt. So voltage across A and D, you see, this is A point, this is D point. Okay. So voltage across A and D is equal to what? 3 volt. That means across A and D, this is one path, this is second path, this is third path. So we can say voltage across this capacitor is equal to 3 volt. Voltage across this capacitor is also 3 volt. Voltage across this capacitor is also 3 volt. And what is voltage across DB? So voltage across DB is equal to 6 volt. That means voltage across this capacitor is 6 volt. Okay. So now we have to find the what is the voltage or what is the charge across each capacitor. Charge across each capacitor. So first you find what is the charge across 3 microfarad capacitance. Charge across 3 microfarad capacitance is equal to CV. Q is equal to CV. So what is the capacitance here? 3 microfarad into what is the voltage across this capacitor? 3 volt. That is equal to 9 microcoulomb. This is the charge across 3 microfarad capacitor. Similarly, what is the charge across 11 microcoulomb? So charge across 11 microcoulomb is equal to similarly CV. C is equal to 11 microfarad into voltage is equal to 3 volt. That is equal to 33 microcoulomb. So this is the charge across 11 microcoulomb. Similarly, what is the charge across? What is the charge across this point, this terminal A and D, this third path? You see, in the third part, there are two capacitors connected in series, 12 and 6. And what is the equivalent capacitance? That is 4 microfarad. So in this path, you find the what is the charge value. So I can write charge across this 4 microfarad, which is nothing but charge across the 4 is nothing but equivalent of 12 and 6. So since it is connected in series, charge across 12 is also same as charge across 6. So which is equal to charge across this 4 microfarad. So charge across 4 microfarad is nothing but charge across 12 microfarad or charge across 6 microfarad. Again, what is the formula? C into V. So what is the capacitance here? Capacitance is equal to 4 microfarad. And what is the voltage across this? Voltage across this is equal to 3 volt. So that is equal to 12 microcoulomb. So this is the charge across 12 microfarad as well as 6 microfarad. So I am writing here the charge across 3 microfarad we got, it is 9 microcoulomb. Charge across 11 microfarad is equal to 33 microcoulomb. And charge across 12 and 6, charge across 12 and 6 is equal to what? 12 microcoulomb. Now see, here 9, here 33, here 12. If we add this, total charge will flow through this 9 microfarad. Okay, so now the charge across 9 microfarad, you see, charge across 9 microfarad is nothing but charge across D and B. So that should be equal to what? That should be equal to the sum of these 3 charges. Because if we apply KCL, Kirchhoff's current law, total incoming current is equal to total outgoing current, or total incoming charge is equal to total outgoing charge. So to this D point, what is the total incoming charge? 9 plus 33 plus 12. So which is equal to 54 microcoulomb. And we have known, so charge through this 9 microcoulomb is nothing but 54 microcoulomb, because we have already discussed charge across A to B is equal to 54 microcoulomb. So which satisfy our answer. Otherwise you can find charge across 9 microfarad. So 9 microfarad is nothing but what? dB. Charge across dB is equal to capacitance across dB into voltage across dB. So capacitance across dB is equal to 9 microfarad. Voltage across dB you have got, 6 volt. So that is equal to 54 microcoulomb. In any way you can solve this problem. Okay, so we got find charge and potential difference across each capacitor and total charge supplied by the source. So what is the total charge supplied by the source? Total charge supplied by the source is equal to 54 microcoulomb. So this is the example 24.8. So we'll find the solution. You see here, what is the magnitude of the electric field required to store 1 joule of electrical potential energy in a volume of 1 cubic meter in vacuum? Suppose this is a capacitor. Inside the capacitor there is vacuum. So if it is vacuum, the relative permittivity is equal to 1. So here, what is the energy stored? Energy stored is equal to 1 joule. And what is the volume of the space? So here volume of the vacuum is equal to 1 cubic meter. So you have to find what is the magnitude of the electric field. What is the magnitude of electric field? So now you see, you know the energy density. U is equal to what? Energy density. Energy density is nothing but total energy per unit volume. So this total energy is equal to 1 joule per meter cube. So this is the energy density. And we know the relationship. The energy density is equal to half epsilon naught into E square. That is equal to E square is equal to 2U by epsilon naught. That implied electric field intensity is equal to square root of 2U by epsilon naught. So this electric field intensity is in what? Is in the vacuum. So I am writing here E naught. So that implied E naught is equal to, just put the data, 2 into U. U is energy density, that is 1 joule per cubic meter, divided by epsilon naught, which is equal to 8.854 10 to the minus 12. So if we will calculate, I think it will come 4.75 into 10 to the power of 5 volt per meter. So this is the energy, this is the electric field. Now question is, Now question is, if the field magnitude is 10 times larger than that, how much energy is stored per cubic meter? So that means the electric field, whatever electric field is now there, if we will increase the electric field by what times? 10 times. Then what will be the energy stored per unit volume? Now see, second bit. So energy density is equal to half times epsilon naught into E square. That means half is constant, epsilon naught is constant. So energy density is directly proportional to E square. Energy density is directly proportional to E square. So here the electric field is increased to what times? 10 times. So if electric field will increase by 10 times, the new energy density will be proportional to 10 times of E whole square. That means U dash is proportional to 100 times E square. Or you can say U dash by U is equal to 100 E square by U is also E square. So that means the new energy density will be 100 times the initial energy density. Okay, so energy density will be increased by what times? 100 times. So initially energy density was what? 1 joule per cubic meter. So now the new energy density will be 100 joule per cubic meter. Now see, this is exercise 24.18. So here do two capacitors, 3 microfarad, 5 microfarad are connected in series to a supply of volt 52 volt. So you have to find charge on each capacitor, what is the charge through each capacitor, and what is the potential difference across each capacitor. Let us say potential difference across C1 is equal to V1, potential difference across C2 is equal to V2. And you know, since it is series connection, charge through this as well as this will remain same. So now we will find the equivalent capacitance of C1 and C2. Since both are connected in series, I can write the equivalent capacitance across which terminal, A and B terminal, is equal to C1 C2 by C1 plus C2. That is equal to 3 into 5 by 3 plus 5. That is equal to 15 by 18. 15 by 8, 15 by 8 microfarad. This is the equivalent capacitance. So now we will find what is the total charge supplied by this source. So you know Q is equal to C into V. So here across A and B, I can write in this way. Charge across A and B is equal to capacitance across A and B into potential difference across A and B. So that implied charge across A and B is nothing but capacitance across A and B is equivalent capacitance, which is equal to 15 by 8 microfarad into voltage across A and B. It is nothing but 52 volt. So just multiply this, you will get 97.5 microcoulomb. So that means since it is series connection, charge through C1 is equal to Q1 is also 97.5 microcoulomb. Charge across C2, which is Q2, it is also 97.5 microcoulomb, because in series charge remains same. Then what is the potential difference across C1? So V1 is equal to Q1 by C1. That is equal to Q1 is equal to 97.5 microcoulomb. C1 is equal to 3 microfarad. Micro cancel. 97.5 by 3 is equal to 32.5 volt. Similarly, the voltage across, potential difference across C2 is equal to Q2 by C2. Q2 is nothing but 97.5 microcoulomb. Capacitance is equal to 5 microfarad. Just divide this, you will get 19.5 volt. Just cross check whether your answer is correct or not. You see the voltage across this is equal to plus voltage across this should be equal to total supplied voltage. So here V1 is equal to, so V1 plus V2 is nothing but V1 is 32.5, V2 is 19.5. So if you add this, you will get 52 volt, which is equal to supply voltage. So now let us solve this exercise 24.35. Question is, a capacitor of capacitance 12.5 microfarad. So this is initially it is given air capacitance. It is connected to a potential source of 24 volt. Now initially this is the situation. After this, with voltage source remaining constant, with that voltage source remaining constant, we will introduce the dielectric. Okay, so this is the first case. Second case, same voltage source, that is 24 volt. So here also 24 volt. So here what will happen? You insert a dielectric medium whose dielectric constant is given by 3.75. So after inserting the dielectric, question is how much energy is stored in the capacitance before and after the dielectric is inserted. So before inserting the dielectric, what is the energy stored? So energy stored before inserting the dielectric is equal to what? Half CV square. C is C naught, V square. So half C naught, it is given 12.5 microfarad into voltage is equal to 24 square. So if you will calculate, it will come 3.6 millijoule. This is the energy before inserting the dielectric. So after inserting the dielectric, what will happen? So here after inserting dielectric, what will happen? Capacitance will increase, because you know capacitance in any medium is equal to epsilon r times capacitance in air medium. So here dielectric constant or relative permittivity is given 3.75, and what was the initial capacitance? That is 12.5. So this is the capacitance after introducing the dielectric. Okay. Then what is the voltage across this capacitor? After inserting the dielectric, voltage remains same. We are not disconnecting the source. So voltage across this is same as that of previous. So voltage is equal to this. So now what is the total energy stored after inserting the dielectric? So here half C V square. So half into C. So C means it is already increased by what? 3.75 into 12.5 microfarad into voltage is same 24 square. So that means only this factor 3.75 times of the previous energy. Previous energy is how much? 3.6 millijoule. So if you multiply this, you will get 13.5 millijoule. So now after introducing the dielectric with same potential difference, the energy will increase from what? From 3.6 millijoule to 13.5 millijoule. So second bit question is, how much did the energy change during the insertion? Did it increase or decrease? So definitely answer is increase. Energy increases. By how much? So final energy is 13.5 millijoule. Initial energy is what? 3.6 millijoule. So if you will calculate, just take the difference. So what is the difference? I think 9.9 millijoule. So this is the increase in energy stored across the capacitor. Now see, test your understanding too. So 4 microfarad and 8 microfarad capacitors are there. In which type of connection 4 microfarad capacitor have greater potential difference across it than 8 microfarad. So you see, suppose there are two capacitors. One is 4 microfarad, another is 8 microfarad. So we can connect both by either in parallel or in what? Series or in series. Okay, so but question is, in which type of connection 4 microfarad capacitor have greater potential difference than that of 8 microfarad. You see, in parallel connection, potential difference across both are same. So we cannot say potential difference across 4 is more than potential difference across 8. So parallel is not possible. So second option is incorrect. Come to series. In series, you know, charge across each capacitor remains same. But what is the potential difference? V is equal to Q by C. Since in both cases charge remains same, so I can say V is inversely proportional to capacitance. So if capacitance decreases, potential increases. So that means the capacitance out of this 4 microfarad is low. So if capacitance decreases, potential difference increases. So we can say potential difference across 4 microfarad is greater than potential difference across 8 microfarad, because with decrease in capacitance, potential increases. So we can say potential across 4 is greater than potential across 8. So this is possible in which case? Series case. So answer is this. Next, so this is the answer. Second bit. Second bit is that in which type of connection 4 microfarad capacitor have a greater charge than 8 microfarad capacitor. So you know what is the formula of charge? Q is equal to C into V. Now see, in parallel connection, you see, so Q is directly proportional to what? Q is directly proportional to C, because V of both are same. So if V of both are same, charge is directly proportional to C. If C decreases, charge decreases. If C increases, charge increases. So but question is, in which type of connection charge across 4 microfarad is greater than charge across 8 microfarad? So this is not possible. We see if C decreases, charge decreases. So that means so charge across 4 microfarad is less than charge across 8 microfarad in which connection? In parallel. Because Q is equal to CV. V is constant. So Q is directly proportional to C. In series what happen? In series, charge across each is same. That means charge across 4 microfarad is equal to charge across 8 microfarad. So in no case charge across 4 microfarad capacitor have greater charge than 8 microfarad capacitor. So in no case. So which is answer? So answer is neither nor. In no. So this is your test and understanding 3. So there are 2 capacitor, 4 and 8 microfarad. So question is, in which type of connection the 4 microfarad capacitor have a greater amount of stored energy than 8 microfarad capacitor? That means you have to prove the energy stored across 4 microfarad capacitor is greater than energy stored in 8 microfarad capacitor. In which case? Suppose I will take parallel connection first. Then I will take series connection. So you see, this is 4 microfarad. This is 8 microfarad. Okay. So now you know what is the energy stored formula? Energy stored is equal to half C V square. So in parallel connection, V is same. In parallel connection, V is same. If V is same, the energy stored is directly proportional to capacitance. If capacitance is low, energy is low. If capacitance is more, energy is more. So here, since 4 microfarad is less than 8 microfarad, so energy stored in case of 4 microfarad is less than energy stored in 8 microfarad. But our question is given, energy stored in 4 microfarad capacitor must be greater than energy stored of 8 microfarad. So parallel connection is not possible. Come to series. In series, charge across each capacitor remains same. So you know the energy stored is equal to formula Q square by 2C. So in series connection, charge remains same. So Q is constant. If Q is constant, energy stored is inversely proportional to C. So if C decreases, energy stored increases. That means capacitance of 4 microfarad is greater than capacitance of 8 microfarad. So which is correct? So correct answer is series. So this is the answer. Now this is test and understanding 24.4. You see, question is given like this. Suppose this is a parallel plate capacitor where there is a dielectric inside the plates. The dielectric constant is K. And let us say charge is Q, here it is minus Q, and the potential difference is say V naught. Okay. So now what will happen? If the dielectric slab of dielectric constant K is pulled out from the capacitor, now what will do? This capacitor, this capacitor will remove the capacitor. If we remove the capacitor, this will be air. So in that case, which if charge do not change, so here charge was Q minus Q, here also charge Q minus Q. Same charge will be there, only dielectric is pulled out. That means here this capacitor is filled with only air. If so, what will happen to the what dielectric slab of dielectric constant pulled out from the capacitor if charge do not change? How does the energy? How does the energy changes in this case? So now you see, so you know what is the formula of capacitance for any medium? It is nothing but epsilon r times capacitance in air medium. That is equal to K times capacitance in air medium. So in the first case, capacitance is say C. In the second case, capacitance is say C naught. So we can write C is equal to K times C naught. So that means C naught is equal to C by K. So here by pulling the dielectric, capacitance decreases. Capacitance decreases. So here charge remains same. Charge is the same, but capacitance decreases. Then what will happen to the energy stored? So energy stored formula is equal to what? Q square by 2C. So here charge in both case is same. So that means since charge is the same, the energy stored is inversely proportional to the capacitance. So if capacitance decreases, energy stored increases. In the second case, when you will remove the dielectric, capacitance decreases. If capacitance decreases, energy stored increases. So this is your answer. So with this, I conclude the chapter 24, that is capacitor. So you enjoy all the videos. Okay, bye.